In this module, we will see a very important class of machines called induction machines. And they are used in very low power to extremely high power applications. And in very low power applications, of course, they are single phase. But in this module and in this textbook, we will basically concentrate on the three phase and single phase later on. So let's start, and we'll assume, of course, a balanced sinusoidal steady state operating condition, and this is in steady state. And first, of course, we'll begin by looking at the structure of these machines, and then we'll also look at part of the principle of operation. We'll go on for 2-3 more modules, but in this module, we will basically assume that the rotor is magnetically present, but somehow it's electrically open circuited. Okay, so let's begin. So just to talk about the applications, they are used in all kinds of general purpose applications where we need to drive something at we don't really care if the speed is exactly what it needs to be. So general purpose. Whereas there are some adjustable speed drives where we do care what the speed ought to be, and we need to vary that speed. So that, in general purpose, of course, it could be running at essentially constant speed. But in adjustable speed drives, we do want to control their speeds. And in servo drives, we may even want to control the position of the load through these induction machines. And certainly, induction machines can be used. So wherever you see motors, think of them as machines, because we will look at them in both motoring as well as generating mode. Okay. So as far as the structure is concerned, just like in this previous PMAC machine that we discussed, these have a three-phase winding as shown here in a simple manner. Each of these phase windings is sinusoidally distributed, ideally speaking anyway, and has n sub s number of turns, and their magnetic axes are 120 degrees apart with respect to each other. Now, there are wound rotor machines, induction machines, but by and large, majority of them are squirrel cage. So that structure is shown here, where there are electrically conducting bars around the periphery of the rotor, and in some slots or something like that. And on the both sides of this rotor, these bars are electrically short-circuited by so-called end rings here. All right, so we will concentrate on squirrel cage induction machines. All right, so now the stator, first let's assume that the rotor is present, but electrically it's open circuited somehow, as if those bars that you saw in the squirrel cage in the previous slide, they were somehow cut, so the current cannot flow. And let's make an assumption initially, and we will include that later on, but let's assume that the stator resistance and the leakage inductance is 0. So it's kind of an idealizing assumption to a certain extent. And we are applying these three voltages across these three windings, balanced sinusoidal voltages. And these would result in magnetizing currents, as we saw earlier, in connection with our discussion earlier in earlier modules. Each of these voltages would result in a magnetizing current IMA, IMB, and IMC flowing. And under this assumption of 0 resistance, these currents would be 90 degrees lagging behind their respective phase voltages. So that's what is shown in this phasor diagram. And these currents would then cause a rotating MMF, rotating flux density distribution in the air gap. And this will rotate at a synchronous speed, omega sync, which depends upon the frequency at which these voltages and currents are applied, but also on the number of poles in this machine. So if it's only a 2-pole machine, then this expression applies. But if you have higher number of poles, p number of poles, let's say, then the synchronous speed is given by this here. So the synchronous speed is inversely proportional to the number of poles. But of course, it is proportional to the frequency of applied voltages and currents. All right. So, we saw this phasor diagram earlier, but we can also represent this in terms of space vectors. So these currents have phase currents have this amplitude for phase voltage having this amplitude here. L sum M is the magnetizing inductance. Then you can see that the current space vector we can generate from this phasor for I sub A. Phasor for I sub A is 90 degrees behind V sub A, which is shown horizontally here. So that's why the space vector has this minus 90 degree here, and the amplitude is larger than the phase amplitude by a factor of 3/2. Okay, so those things are included here, and you can also see that we can represent these phase voltages by a stator voltage space vector here, which again would have an amplitude 3.5 times larger than the amplitude of the phase voltage here. Here's the phasor diagram for phase A. Correspondingly, there's an equivalent circuit here, and this flux density distribution that is produced by all these 3 phases combined has a constant magnitude and rotates at the synchronous speed omega sync over here. So in this diagram at t equal to 0, if voltage at in phase A is peaking, then V sub S space vector is along the horizontal line, and IMS is 90 degrees behind it. And similarly, this flux density space vector is collinear with the stator current space vector, and all these vectors are rotating in steady state at this speed omega sync. So we need to convince ourselves, and you can also see what the peak flux intensity is in the air gap, and similarly what the peak flux density of the distribution. This is the flux density space vector, and we can see that its amplitude, it's just mu naught times the field intensity, and so we can write this as flux density space vector as well. All right. So this brings us to the summary of this module. There's not much in it. That we first saw the application of these induction machines from very mundane application to wind turbines, for example. A lot of wind turbines using induction machines as generators. We looked at their structure. That at least in one form, we have a squirrel cage rotor, but certainly there are wound rotor induction machines as well. And then we looked at the principle of operation, where the rotor is electrically open.